Hello students, welcome to Ohm Institute. Myself Hemanth, Faculty of Digital Circuits and EMF at Ohm Institute. In this video, I'll discuss about the previous year questions of KPTCL as well as KPSC. Generally, from the student point of view, people assume that EMF is a tough subject, due to which people used to leave this subject completely. But if you look at the previous year questions of KPTCL, the kind of questions you are having in EMF are easy to moderate questions. So, since most people will leave this subject, if at all you prepare this subject properly, I am 100% sure that you will have edge over others. And the amount of weightage for this subject in KPTCL is nearly something around 5 to 6 marks. And coming to the syllabus we are having for KPTCL in the subject of EMF, initially we are having vector algebra as well as coordinate geometry and vector calculus. And furthermore, the direct questions we had in the previous years is only from vector algebra. So only from vector algebra we are having a direct question. Okay. Only from this topic we are having a direct question. Whereas from vector calculus we are having many indirect questions, in the sense that the question may be a part of electrostatics or magnetostatics, but still basically it's a vector calculus question. Okay. So because which we are having a few questions, indirect questions from vector calculus. Okay. And the study of coordinate geometry is always required for us to solve many other questions. So even coordinate geometry, the questions are indirectly based. Okay. And coming to the second topic is electrostatics. We had almost 11 questions, 11 previous year questions from electrostatics itself. Okay. So from weightage point of view, every year you may expect one question from electrostatics at least. Next we have magnetostatics. Again, from weightage point of view, magnetostatics is having a very good weightage of nearly something around 14 questions. 14 questions are from magnetostatics topic. And then we have time varying fields as well as Maxwell's equations. And again, from weightage point of view, the weightage is not so great. Almost we are having something around 3 to 4 questions. We had something around 3 to 4 questions, from the Maxwell's equations as well as time varying fields. Apart from these, whenever we discuss the topic of electrostatics itself, a part of that is nothing but electrical materials. And furthermore, whenever we are discussing about magnetostatics, there also we can discuss about magnetic materials. Okay. And then surprisingly, we had a couple of questions in the previous years from EM waves. EM waves as well as transmission lines, they are not part of electrical syllabus usually. They are part of EC paper. But if you look at the previous papers, we had seen almost 2 questions from EM waves and 1 question from transmission lines. And the kind of questions you are having from these subjects or from these topics, they are of very easy nature. So this is the broad syllabus you are having in case of KPTCL. And like I told, from weightage point of view, a good amount of weightage is with respect to electrostatics as well as magnetostatics. And after that, a good weightage is with material science, which is nothing but electrical as well as magnetic materials. Okay. Even though we could see that magnetic materials is a part of the syllabus, but still we had a good number of questions in the previous years from electrical materials also. Okay. So let's look at the questions in the same order. First, we look at questions from vector algebra. So here we are given 2 vectors, which is a bar as well as b bar, and we are supposed to take the cross product of both the vectors. It's a pretty simple question, a class 12 question I could say. So we have a bar cross b bar. This is what we are supposed to find out. Okay. So we can write this as, this is 2 ax cap can be written as simply x cap in short form, and plus 4 ay is given to us, so 4 y cap, and minus 3 z cap cross. The second vector given to us is ax. Ax is nothing but we can write it as x cap, minus ay can be written as y cap. Okay. And we are supposed to use the basic cross product rules, which says that x cap cross x cap is also equal to y cap cross y cap is also equal to z cap cross z cap. Z cap cross z cap. and all of them are equal to 0 only. And furthermore, we have vectors in the cyclical fashion. So x cap cross y cap is equal to the third vector, which is z cap, and the second cross third, which is y cap cross z cap, becomes equal to x cap, and the third cross 1, which is z cap cross x cap, becomes equal to the second, which is nothing but y cap. And if at all here, if you interchange the order of vectors, in that case we will have on the right side also a minus sign. So let's do the calculation here. What do we get? We have 2 into x cap cross x cap becomes equal to 0, x cap cross minus y cap becomes equal to, we know that x cross y is z, so x cross minus y is minus z. So 2 into minus z cap. Now we will take y into x cap. Y into x becomes equal to, if you look at x cross y is z, so y cross x will be equal to minus z. So we will have plus 4 into y cross x is minus z cap. And y cross y becomes equal to anyway 0, we don't have to bother about that. And lastly, we are having with respect to z, so minus 3 into z cross x. If you look at z cross x is nothing but y, so this is y cap, and then we have minus of z cross minus y cross z is equal to x cap, and z cross y becomes equal to minus x cap, and anyway we are having minus sign there, so this becomes equal to plus minus 1 into, we have minus x cap, okay, because z cross y becomes equal to minus x. And ultimately, whenever you simplify this, what do you get now? This is minus 2 z cap and minus 4 z cap, and minus into minus is nothing but plus. We have x cap into minus 3, so this is minus 3 x cap and minus 3 y cap, and finally this becomes equal to how much? This is minus 3x cap minus 3y cap minus 6z cap. This is our answer. If you look at the options, we have minus 3 and minus 6 as the first option. Okay, a pretty simple concept here, nothing great. All we are supposed to remember is nothing but this particular relations that we have with respect to cross product of vectors. Okay, let's go to the next question. In the next question, the electric field inside a hollow conducting sphere. Okay, so we are taking a hollow conducting sphere. So this is a hollow conducting sphere. So whenever we have a hollow conducting sphere, we are supposed to find out what is the electric field inside. Electric field inside this particular hollow conducting sphere. Okay. Now inside hollow conducting sphere, if you look at, it depends on the diameter of the sphere. First option. Second option, varies according to the direction of Earth's magnetic poles is 0. None of this. Inside hollow conducting sphere, electric field is always equal to 0. Okay. So electric field is always equal to 0. Where? Inside. This is inside. Okay. But rather, potential is a constant value. In this case, since electric field is equal to 0, potential becomes constant. So if this is a question of electric potential inside hollow conducting sphere, so in that case the answer is it remains constant. But whereas electric field inside hollow conducting sphere remains to be equal to 0. Okay, so the answer is 0. Let's go for the next question. Yeah, a charged sphere of radius a with a volume charge density of rho v coulombs per meter cube. So we are supposed to find out flux density at a distance of r less than a. So we are having some charged sphere. This is a charged sphere, and the radius of this charged sphere is nothing but, this is we are having the radius as a. So this is a volume charge. This is a volume charge. And in case of this particular volume charge, the charge density, which is nothing but rho as a function of r, is given as, this is rho v. And in fact, I could say that this is a constant value. This is a constant value. And we are supposed to find out at a distance of r less than a. At a distance of r less than a. So let me draw the second guy. The second sphere we are taking is this sphere having a radius of r, wherein the value of r is less than a. Now we are supposed to find out at this particular distance from the center of this particular sphere, what is the value of flux density. We are supposed to find out what is flux density. So what concept we can use here? See, here the examiner is testing the concept of Gauss law. Okay, so we are supposed to answer this question by means of Gauss law. Typically, whenever you practice these kind of Gauss law application questions, now I'm very sure that this question is a piece of cake for many students. But if you are not practicing these kind of questions, in that case, from the options it looks like as if this is a very tough question. But in general, this is not at all a tough question. So what we can do is, at a distance of r from the center, we can take the Gaussian surface. So this is the Gaussian surface. Gaussian surface is a symmetrical surface taken symmetrically with respect to the charged body. So we have taken the Gaussian surface also with the center of the center coinciding with the center of the charge density. So in this case, we are supposed to find out what is the value of charge density or the value of flux density. So whenever you apply the Gauss law says that the outgoing flux, the outgoing electric flux becomes equal to the charge enclosed. Outgoing flux from the Gaussian surface, enclosed charge within the Gaussian surface. And whenever you calculate how much is the value of flux going out of the Gaussian surface, see, flux is always equal to flux density into area. So let me call that flux density as nothing but d. And through what area the flux is going out? The flux is going out of the surface area of this sphere. And what is the surface area of the sphere? The surface area of the sphere is 4 pi r square. And this becomes equal to the charge enclosed. And how much is the value of charge enclosed here? Charge enclosed becomes equal to the charge density rho v into the volume enclosed. And in this case, what is the value of volume enclosed? The volume is volume of sphere, which is 4 by 3 pi r cube. 4 by 3 pi r cube. So on left hand side as well as right hand side, we can cancel out 4 pi as well as 4 pi. R square and cube both are gone. And finally, we have the answer to be equal to charge density, flux density is equal to, this is rho v into r by 3. Rho v into r by 3. Okay. And the answer for flux density is in terms of coulombs per meter square. So if you look at the options, we have the option of rho v into r by 3. Sometimes even if you don't know the formula, you can always cross verify the answer from the options. Now understand one thing, 0 is not the answer. Why is that so? 0 is not the answer because it violates the Gauss law. If you know the basic Gauss law, flux is coming out indicates we have to be having some charge, or vice versa. Charge is there. Whenever we are having some charge inside this region, definitely flux also should be coming out. So since flux is coming out, flux density can't be equal to 0. So 0 is not the correct answer. Okay. If you look at the units for this, units for rho v into r by epsilon. What is the units for rho v? It is coulombs per meter cube. And what is r? It is meters divided by, we are having units for epsilon. What are the units for epsilon? Units for epsilon is in terms of farads per meter. So this is farad per meter. And whenever you calculate this, what do you get now? The answer is nothing but coulombs per meter square divided by farads per meter. But what are the units of flux density? The units of flux density itself is nothing but coulombs per meter square. So apart from coulombs per meter square, you are having some extra term in the denominator. So it indicates what? Obviously this option is wrong. Same story is also true with option D. In option D also, you are having in the denominator epsilon term. So because of that epsilon term again, obviously the units will not match for us. So in only one option the units matches for us, and that is in option A. And that is nothing but answering the question through units, and whatever procedure we followed here, this is solving the question by the actual process. Okay. So let's go for the next question. Yeah, electric field due to a sheet of charge is given by dash. Here, whenever the examiner uses the term electric field, the examiner is meaning electric field intensity. Okay, electric field intensity. Okay, and here all we are supposed to find out is what is the magnitude of electric field intensity. And we know that electric field intensity E is equal to flux density by epsilon. Okay, flux density by epsilon. And for the sheet charge, what is the electric flux density? It is half of surface charge density. And what is the charge density? Whatever is rho s term that is being mentioned here corresponds to the standard notation of surface charge density. So this is rho s by 2. Okay, rho s by 2 is nothing but the surface charge density divided by rho s itself is surface charge density, rho s by 2 is flux density, electric flux density, and by epsilon is nothing but electric field intensity. So rho s by 2 epsilon finally becomes equal to the electric field intensity for infinite sheet charge. Okay, so if you look at the options, we are having rho s by 2 epsilon. The option D is nothing but the correct answer. Okay, let's go to the next question. Yeah, the divergence of electric field intensity at any point equals dash. This is the first Maxwell's equations we are having. The first Maxwell's equation says that del bar dot d bar corresponds to rho v. And how do we obtain this particular first Maxwell's equation? We can obtain this by means of again Gauss law. So if you look at most of the questions we are having in electrostatics are primarily based on Gauss law. Okay, so we can say that Gauss law says flux coming out is equal to the charge enclosed, and mathematically what is the flux coming out of a particular closed surface? We can write it as the closed surface integration of d bar dot ds bar, and becomes equal to, this is rho v times dv over the volume enclosed by the surface S, the closed surface S. And by applying the divergence theorem, we can replace the left hand side expression by means of d bar dot ds as del bar dot d bar into dv over the volume enclosed by S, and this becomes equal to RHS value of, this is rho v into dv of volume. Now furthermore, whenever you equate the LHS as well as RHS, we can say that del bar dot d bar becomes equal to rho v, Now LHS is what is given in the question, the divergence of electric field intensity. Okay, in fact they have asked divergence of electric field intensity at any point equals to dash. So how do we convert D into E? We can rewrite this expression as del bar dot epsilon times E bar, because D is equal to epsilon times E becomes equal to rho v. If nothing is mentioned in the question, we can assume that the material is isotropic as well as homogeneous, and hence epsilon is constant. We can take this epsilon outside. So finally what we have is del bar dot E bar becomes equal to, we can take this epsilon to the RHS, so we'll have this expression as rho v by epsilon. So del bar dot E bar becomes equal to rho v by epsilon. So if you look at the options, it is nothing but 1 by epsilon times the volume charge density at that particular point. First option says integral, we don't have any integration here. Epsilon naught times into, obviously not correct. It's equal to directly the volume charge density at that point. It would have been the answer D would be the correct answer, whenever instead of electric field intensity the examiner told electric flux density, like whatever we have written here. Okay, but since they have asked electric field intensity, whether we are supposed to choose this expression or this expression, the answer is this expression. And on the basis of this, what is the value of del dot E? Del dot E is equal to 1 by epsilon times rho v, and hence the option is option B. Okay, let's go to the next question. The electric field intensity and potentials are related by what formula? So here electric field intensity is given by E bar and electric potential is given by V. So E corresponds to electric field intensity and V corresponds to the electrostatic potential. E and V are related by two expressions. One of the formula is nothing but E bar becomes equal to negative gradient of V. This is one formula. And one more formula is V is equal to minus of integral E bar dot dl bar. Okay, so these are the two formulae which links V as well as E. And if you look at the options, one of the option we have is nothing but E bar is equal to minus del bar V. The answer is nothing but D for us. So if you look at the kind of questions we are having in EMF are more or less straightforward formula based questions. So very few questions we have are analysis based questions. Going to the next question. The total electric flux through any closed surface surrounding charges is equal to the amount of charge enclosed. The above statement is associated with dash. Like we have discussed many times till now, whatever statement that is given to us is nothing but the Gauss Law. This is the Gauss Law, which says that the electric flux coming out of any closed surface is equal to the charge enclosed by the closed surface. And in terms of equation, we can write this as the total electric flux phi E coming out of S corresponds to, this is integration of rho v times dv. Rho v dv is nothing but the total charge enclosed in a particular volume. And what is that volume? The volume enclosed by the closed surface. So whatever statement given to us is nothing but the Gauss Law. Okay, let's go to the next question. Two parallel plates are separated by a distance t and they are charged to a voltage V. The electric field is given by dash. So whenever we have a parallel plate capacitor separated by a dielectric medium, so we are having two parallel plates, and the first guy is the top plate and the second guy is the bottom plate. So this is the top plate and this is the bottom plate. Separating both the plates is dielectric medium. Okay, and let's assume that the potential difference between the top plate as well as bottom plate is equal to V, and they are separated by a distance of d. In this case, examiner used the notation of capital D. Okay, so this is what is given to us, and we are supposed to tell how much is the electric field we have in between both the plates. Let's assume this is the plus Q charged plate and this is negatively charged plate. Now we know that electric field goes from where to where? Always from high potential to low potential or positive charge to negative charge. So because which this is the direction of electric field we are having. So if you look at in the space of dielectric medium, we are having some electric field, and what we are supposed to find out is what is the value of this electric field. Okay, and the magnitude of electric field inside a parallel plate capacitor is a constant value, and that constant value is given by, this is potential difference by distance between the plates. Okay, potential difference by distance between the plates. And furthermore, this question also, like in the previous question, you can simply answer that if you know the units of electric field intensity. And what is the units of electric field intensity? We are supposed to find out electric field intensity. The units is given by volts per meter. What is the units of distance? This is meter. What's the distance of voltage? It is nothing but volts only. Now let's see what are the units of all the options. In the first option we are having V into D. V into D means what's the units now? This is volt meter. This is volt meter but not volt per meter, and hence option A is wrong. Option C says what? This is volt into distance square. So this is voltage into meter square. Again, not the answer for not the units for electric field intensity, gone for us. Option B says what? This is volts per meter. Could be the answer. Could be the answer. I cannot say that if I am only verifying with respect to options or units. In that case, I can't exactly conclude that okay, B is the answer. We have to verify even the other option. And the last option says that volt square per meter. So this is volt square per meter. Again, obviously not the correct units. So even if I don't know this particular formula, still I could answer only from units, because I ruled out that A is not the answer, C is not the answer, D is not the answer. Answer has to be D. Okay. But if you know the concept anyway, so in that case, surely you can say that the answer is nothing but D. But since anyway we are discussing this particular concept, let me discuss about one more point, because we have one more question on the same topic. That is nothing but here inside the dielectric medium, whatever electric field we are having E bar, this is constant. This is constant. That is, at every location inside this dielectric medium, you take various points. Let me take this point as nothing but point 1, let's say. So I am taking this as somewhere randomly. I am taking this is point 1, this is point 2, this is point 3, this is point 4. Randomly I have taken 4 points. At all these points, what is the value of electric field intensity? Remains exactly same, which is equal to V by D. Okay, because in case of parallel plate capacitor, electric field intensity or dielectric stresses inside the parallel plate capacitor remains always constant. Okay. Yeah, this is what is the question, which is application of the previous question. Okay. Now here what is given to us is nothing but we are having some positive plate and we are also having some negative plate, and we are having some potential somewhere on the outside of the plate, but doesn't matter anyway. So electric field is created by two parallel plates. So we are having one parallel plate, one more parallel plate. I don't care about this minus 40 volts. Okay. All I could see is I'm having some plus Q here, as well as I'm having some negative charge on the other plate, and we are supposed to find out at which of the following points is the electric field the strongest. So we are supposed to find out in between A, B, C as well as D at what point the field strength is more. Now if you don't know the concept, there is a very good chance that you will do a mistake in this question, because you assume that now point D is very close to the source, which is minus 40 volt source. So because which point D might be having more electric field strength. But understand that all the 4 points given to us, they are inside the dielectric material only. That is, they are within the parallel plates only. So because of that, electric field E bar inside the parallel plates remains constant everywhere. Whenever we say constant, it is constant with respect to space. So because of that, first option says that electric field is the same at A and B. No, the electric field, yeah, in fact A is also correct. The electric field is the same at C and D points. Electric field is greater at A than B. Electric field is same at all points. Obviously, the electric field is same as all points. If you look at technically, even option A as well as option B are also correct. Okay, but they are only covering one half of the points. They are saying that electric field remains same at A and B, but no information regarding C and D is given. And in option D, vice versa, information regarding C and D is given, but not A and B. So because of that, technically even A and B are correct, but the most appropriate answer is nothing but in this case option D. Okay. So let's go for the next question. Yeah, which of the following represents the electric field mapped due to a single positive charge? And here the concept we are supposed to know is electric field is always a radial field. This is a radial field. Okay. So electric field flows radially outward of a positive charge and radially inward to a negative charge. And if you look at the charge given to us is nothing but a positive charge. So the direction of electric field has to be radially outward. That is in the direction of radius, but rather outward. And obviously option A is wrong. Option according to that. Option C is also wrong. Option B and C, if you look at, both are nothing but radial field lines only, but this is radially inward. So this guy is radially inward, whereas option B is, if you look at this option, this is radially outward. And hence answer B is the correct answer for the given case, because the charge given to us is positive charge. If at all the charge given is negative charge, in that case D would have been the correct answer. So because of that, even though these are the directions of field lines for charges, this is the direction of field lines for the charges. If at all the charge is negative charge, but since the question is about positive charge, this D option is also the wrong option. Okay. Yeah. In the above diagram, the magnitude of electric field at point A is E. What is the electric field at the point B in terms of E? Okay. So if at all I take this distance as nothing but whatever is the line shown to us, this is 1 unit. So this becomes equal to, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay. So this is what we have. Now what we are supposed to find out is what is the electric field at point B in terms of E, and what is E? E is nothing but electric field at the point A for us. Okay. Now we are supposed to know that because of a point charge, electric field E is proportional to 1 by r square. Okay, proportional to 1 by r square. And if you remember the formula, it's even more good thing. The formula for electric field E due to a point charge is given by Q by 4 pi epsilon r square. So this is the formula we have of electric field due to a point charge. Again, it clearly shows that E is proportional to R square. So I would say that EA by EB is equal to, this is RB square by RA square. How much is the distance of point B? It is nothing but 3 units. So because of that, this is 3 square. How much is the distance of point A from the charge? It is nothing but 1. So this is 1 square and becomes equal to how much? 9. And what is the value of electric field at the point A? The electric field at the point A is given by E. This is called as E for us. So because of that, now what is the answer we are having? What is the value of EB now? EB becomes equal to, the numerator is nothing but A by whatever is this term, which is 9 for us. So EB becomes equal to E by 9. So it becomes 1/9 as compared to the electric field at the point A. So the answer is nothing but A. Okay. See, even if you don't know the concept, if you understand the basic concept is, as you're moving away from charge, field intensity should reduce. So because of that, option B and D are wrong answers, because option B and D says that at a far away point electric field intensity is more. Cannot happen. Okay. Now if you remember that electric field is proportional to 1 by R square, so in that case definitely you'll mark the answer as nothing but A. Okay. But if you don't remember that particular formula, which is E proportional to R square, in that case at least you have to choose between A and C. Okay. Now furthermore, since we are discussing about this concept, you should also know that in case of a point charge, the expression of potential is given by, this is Q by 4 pi epsilon times R. Q by 4 pi epsilon times R. Okay. So here again V, which is potential, is proportional to 1 by R. Electric field intensity is proportional to 1 by R square, whereas electrostatic potential is proportional to 1 by R. So since this kind of a question is already asked, there is a chance that you will get a question on the potential again. Okay. So remember that field intensity proportional to 1 by R square and potential is proportional to 1 by R. Okay. Yeah. If an isolated conducting sphere in air has a radius of 1 by 4 pi epsilon naught. Now given this data, we are supposed to find out the capacitance. The capacitance due to an isolated conducting sphere is given by, now the formula for capacitance is, this is 4 pi epsilon naught times radius of that conducting sphere. And in the given case, the radius is given as 1 by 4 pi epsilon times. And because of that, if you cancel out both the terms, we are having the answer as 1 farads. The answer is 1 farad. Okay. So this is what we have. If you get the answer, it is nothing but 1. Okay. Okay. With this, the questions on electrostatics are complete. Yeah, I think we have one more question. Yeah, this is the last question we have in electrostatics. A non-uniform electric field is represented by equipotential lines. A positive charge with a magnitude of 1 microcoulomb moves in the following path. So the charge is going from where to where. Initially it is at point A, and then it is going to B, and after that it is C, and then D, and then E, and lastly again back to A. So this is the direction, the path the charge is moving. Now we are supposed to find out how much is the work done by the electric field. We have to know that electric field is a conservative field. Electric field is conservative field. Okay. So since electric field is conservative field, whenever any charge moves in a closed path, work done in moving that particular charge along a closed path. If it is an open path, maybe we are supposed to spend some work or spend some energy. But whenever the charge is moving in a closed path, in that case, the work done becomes equal to 0. So because of that, work done in moving the charge, along a closed path, is equal to 0. Okay. So since whatever is the path given to us is again the closed path. How can you say that this is a closed path? Because the initial point as well as the final point both are same, and hence this is a closed path, and hence the work done is equal to 0 microjoules. Okay, a very simple question, but rather this is a conceptual question. You have to know that electric field is a conservative field, because of which the work done in moving the charge along a closed path becomes equal to 0. Okay, yeah. Next, which of the following laws of electromagnetic theory is associated with the force experienced by two loops of wires carrying currents? Okay, and the answer is nothing but Ampere's law. Because whenever you take any conductor, let's say instead of loop I'm taking a conductor, this is a conductor and this is one more conductor. Whatever applies for a conductor also applies for a loop. So it is carrying some current I. Now we have to find out at this particular distance, that is in the presence of second conductor, that is in the region of second conductor, what is the magnetic field produced by the first conductor. Let me call this as 1 and this is 2. Okay, so we want to find out what is the magnetic field produced at this particular location. Let me call that as nothing but H. Okay, since this is the magnetic field produced by the first conductor, let me call it as H1. Now how do you find out this value of H1? We can find out the value of H1 by means of Ampere's law. By means of Ampere's law, we can say that H1 is equal to I by 2 pi r, wherein r corresponds to what? The distance between both the conductors. And once you know what is the value of magnetic field intensity, can you calculate what is the value of force? Yes. By using what formula? By using the formula of F equal to VIL, where flux density, magnetic flux density corresponds to what? This is mu times H. And do you know the information of H? Yes. You can find out the value of H by the previous formula. And from this, if you observe, we can find out what is the force acting on the second conductor because of the first conductor. And by using the same logic, we can also do the reverse. What is the force acting on the first conductor because of the second conductor? And because of this, the answer is Ampere's law. By means of Ampere's law, we can find out what is the magnetic field intensity, and hence we can find out what is magnetic flux density. And by means of magnetic flux density, we can find out what is the force acting on the second conductor. Okay. Yeah, Ampere's circuit law can be mathematically given by dash. So if you look at this, is again a straightforward formula related question, which is nothing but Ampere's law question. Okay, in electrostatics we are having Gauss law. So equivalent of Gauss law in electrostatics is nothing but Ampere's law in case of magnetostatics. Okay, and what does Ampere's law says? Ampere's law says that the closed path integration of magnetic field intensity becomes equal to the current enclosed by the closed path. So whenever you take any closed path, so what is the value of h bar dot dl bar? The circulation of magnetic field intensity along a closed path called as L becomes equal to the current enclosed. The current enclosed by whom? By L. Okay. So this is what is the Ampere's law in the form of equation. Okay, in the form of equation. So this is our Ampere's circuit law. So if you look at the options, we have the option A is h bar is equal to I, wrong. Closed path integration of h bar dot dl bar is equal to I, which is correct. Third option says h cross I is equal to 0. We don't know about this particular option. And option D says h dot I is equal to L. Again, the wrong answer. Here also, if at all you note the units properly, in that case you can eliminate at least 2 of the options. What are the units of H? The units of H is nothing but amperes per meter. Current units is what? Amperes. DL or length units is what? DL or length units is nothing but meters. So if you look at option, first option says what? Integration of h bar. Now integration is done with respect to what? We don't know. Becomes equal to I. Is it a correct answer? No. Since we are having h bar, left hand side units is nothing but amperes per meter. Right hand side units is nothing but amperes. So they are not matching. A is not the correct answer. B, if you look at, what about LHS? H bar units is amperes per meter. Length units is meter. Amperes per meter into meters is nothing but amperes. That's what we have on the right hand side, current. What about option C? Option C, since right hand side is nothing but 0, we can't conclude whether C is the correct answer or not. And what about D? D, if you observe, h dot I. What are the units of h? It is ampere per meter. I is what? Amperes. So LHS units is what? Amperes square by meter. What about RHS units? It is meters. Obviously they are not matching. Option D is also wrong. So we have to choose between B and C, and we can observe that I don't know whether C is correct or wrong if you are verifying by options, but if you are verifying by units, 100% I can say that B is the answer. So because which we can go for the answer B. But anyway, the procedure or the formula is nothing but this is a formula which states that what is Ampere's law for us. Okay. Which of the following laws relates the magnetic field to the magnitude, direction, length and proximity of electric current? And let me tell you, the answer is nothing but Biot-Savart's law. Biot-Savart's law says that, let's assume that you are having a conductor. This is a conductor carrying a current of I. Okay, so this is a current carrying conductor. And this current carrying conductor produces a magnetic field around this particular conductor. And I am taking some random point in space. And let me call that point is nothing but this is the point we are taking in space, point P. Now at this point we want to find out what is the value of magnetic field intensity. But since the conductor we have taken is an arbitrary conductor, a random conductor, we will take a very small section on this particular conductor. And this small section is having a length of dl bar. In the direction of dl bar is the direction of current itself for us. And we are taking a radial vector. The radial vector, from the differential length we have taken as well as the point of interest for us. And let me call this vector as nothing but r bar. Angle made by this particular differential, this particular conductor with respect to r bar, radial vector is nothing but, let's call it as alpha. Okay. So in this case, the Biot-Savart's law says that dh bar, which is differential magnetic field intensity at the point P, dh bar at the point P is given by dh bar is proportional to I dl bar. That is nothing but it is proportional to length of the conductor as well as the strength of the current that is flowing through the particular conductor, and dh bar is proportional to sine of alpha. The sine of alpha, that is the orientation between this particular radial vector as well as the conductor, also is of interest for us. And furthermore, this dh bar is proportional to 1 by r, wherein r corresponds to magnitude of r bar, that is this particular distance. Okay, so combinedly what we are having is Biot-Savart's law says that dh bar is proportional to I dl bar sine alpha by r. Okay, so this is what the Biot-Savart's law tells us. So if you look at that is what is being asked for us. What is the following laws that relates magnetic field intensity to the magnitude, direction, length and proximity of electric current? Okay, so magnitude of electric current is I, proximity of electric current is R, the length of electric current is nothing but dl bar. So because of that, obviously the answer is Biot-Savart's law for us. Okay, so this is one of the very basic laws we are having in case of magnetostatics. Electrostatics, we have two basic laws. The first is Coulomb's law and one more is Gauss law. And in magnetostatics we are having two basic laws, Biot-Savart's law, which is equivalent of Coulomb's law in case of electrostatics, and also we are having Ampere's law, which is equivalent to the Gauss law we are having in electrostatics. Okay, yeah. Steady state magnetic fields are governed by dash law, and the options are Biot-Savart's law, Ampere's circuit law, and both A and B, none of these. And just now I told you that now in case of magnetostatics we are having two basic laws. The first is Biot-Savart's law and the second is Ampere's circuit's law. So because of that, if you look at both A and B are the correct answers, and hence the correct answer is nothing but C. A as well as B, they are partially telling you the answer, whereas C completely specifies the answer. So the most appropriate answer in this case is nothing but C first. Okay, so the answer in this case is C. Okay, yeah, the magnetic flux at a point, the magnetic flux density at a point at a distance of r due to infinitely long linear conductor is dash. So if you forget this formula also you can derive. So let's assume this is infinite conductor carrying a current of I, and we know the direction of magnetic field because for any current carrying conductor follows the right hand thumb rule. So I can say that this is the direction of magnetic field lines, at least one of the magnetic field lines, and let me call it as h bar. And the distance of this magnetic field line from the center of the conductor, let's say, is nothing but the distance is given as capital R. Okay. Now what you can do is you can apply Ampere's law. You can apply Ampere's law on this particular path. Ampere's law. Now whenever you apply Ampere's law along this particular path, what do you get now? It is integral of h bar dot dl bar becomes equal to current enclosed. Now this is closed path integration. So what is the value of h bar dot dl bar along this circular path? This is h into distance. What is the distance or what is the length of this particular path? The length of this path is the perimeter of circle, which is 2 pi r. Right hand side, what do we have? Current enclosed. What is the current enclosed by this particular path? There is only one current carrying conductor carrying a current of I, and hence it is I plus. Okay. And on the basis of this, if you look at what is the value of h, h becomes equal to I by 2 pi times r. So I by 2 pi r is the answer for us. And this is h. In the question we are asked to find out what is b. B is equal to mu times h becomes equal to mu I by 2 pi r. Mu I by 2 pi r. Okay. And if you look at the options, where do we have? Yeah, option C is mu I by 2 pi r. And this is again a application of Ampere's circuit law. Okay. See, if you look at the questions, the kind of questions, we are having very basic applications of Ampere's circuit law as well as the Gauss law. Okay. Sometimes the law directly is asked or the application of that particular law is asked. Okay. Yeah. Next, which of the following is not a source of magnetostatic field? A magnetostatic field have a few sources. Let's see what are the sources of magnetostatic field. Okay. The first source of magnetostatic field is nothing but a permanent magnet. Okay. A permanent magnet. This is the first source. The second source is a current carrying conductor carrying a constant current. So a current carrying conductor. A current carrying conductor carrying a constant current. Okay. And the third is a linearly varying electric field. Okay. A linearly varying electric field. These are the three sources we have for the case of the source of magnetostatic field. So if you look at a DC current in a wire, see a DC current in a wire obviously is nothing but a current carrying conductor carrying a constant current, and hence option A is correct. And the permanent magnet, if you look at, that's what we have told first, a permanent magnet is a source of magnetostatic field. Option C says accelerated charge. Accelerated charge also produces magnetic field, but that's not a magnetostatic field. That is a dynamic magnetic field. That is a time varying magnetic field. It produces a time varying magnetic field. Okay. So because of that, option C is not the what was asked is not a source of, you know, yeah. So obviously this guy is not a source of magnetostatic field, but this is a source of time varying magnetic field. And option D is nothing but electric field linearly changing with respect to time. Again, that's what is the third point we have mentioned. So even the third option is nothing but a source of magnetostatic field. But since it is asked for us what is not a source of magnetostatic field, I would say that the answer is accelerated charge. Accelerated charge is not a source of magnetostatic field, but rather it is a source of time varying magnetic field. Okay. Yeah. Two identical coaxial circular coils carry the same current I, but in opposite directions. So let me draw that. So this is one coaxial circular coil, and since it is told to us that the circular coils are coaxial, so I have to take one more coil whose center is aligned with the first coil, and both are carrying currents, but rather in opposite directions. So if I take the direction of current in the first coil as nothing but something like this, in case of the second coil, this is what is the direction for us. Now we know that whenever you curl your fingers of your right hand in the direction of current, the direction of thumb indicates the direction of magnetic field. So at the center point, So at the center point, what is the direction of magnetic field because of the first coil? Let me call this as first coil, this is the second coil now. Now the direction is nothing but upward direction, which is H1 bar. And dimensions as well as current carried by that particular coils are exactly one and the same. Okay, so since upward direction we have, let me call this direction as Z. Okay, so how can you write H1 bar as, H1 bar can be written as, this is H into Z cap, which is along the positive Z direction. And what is the magnetic field produced by the second you can say coil now? Again, you follow the right hand thumb rule. I am curling my fingers in the direction of current, thumb indicates the direction of magnetic field. So at this point, because of the second coil, the direction is downwards. I'll call it as H2 bar. But since the dimensions of the coil as well as the current carried by the coil remains exactly same, H2 bar becomes equal to, this is H into minus Z cap, and we are supposed to find what is the net magnetic field intensity at the center. Now what is the answer? It is H bar becomes equal to, this is H into Z cap plus H into minus Z cap. Okay, and finally what will happen? Both are cancelled out and you are having 0 bar. So because of that, if you look at the answer is nothing but 0. The net magnetic field produced at the center because of two coils carrying current in opposite directions is nothing but 0. So this is the first part of the video wherein we have covered the topics of vector algebra, vector calculus, electrostatics as well as the magnetostatics. In the second video, we will be covering the rest of the topics, which are time varying fields as well as Maxwell's equations, the electrical as well as magnetic materials, and we also have EM waves as well as transmission lines. So these topics will be covered in the second video. Okay, thank you.